In this course, we will learn the workpiece materials. In metal cutting, workpiece material is one of the most important parameters affecting productivity and dictates the selection of machining setup and process parameters. There are various types of materials, with completely different properties and machinability. ISO classified the engineering materials into 6 material groups based on their properties and machinability, in order to facilitate the process of choosing the appropriate cutting tools and machining parameters for them. Properties essentially determine how the material reacts to being machined, and how in turn machining affects the cutting tool. The table on the screen shows the details of these material groups. When choosing a cutting tool for these materials to machine, a selection is made by considering the ISO standard. Steel is the largest workpiece material group in the metal cutting area. Steels can be non-hardened or hardened and tempered with a chameleometrian hardness of up to 400 hardness Brinell. Steel is mainly an alloy of iron and carbon, which may include other alloying elements as well, in order to obtain enhanced physical properties or machinability. The machinability range of steel materials is very wide according to their chemical composition and heat treatment conditions. In the tables that can be seen on the screen, cutting speed values suitable for carbide inserts are given for 3 different steel materials that are used extensively in the manufacturing sector. These cutting values are average values and can be changed by the manufacturer depending on the cutting conditions. For example, since steel 1020 has a low carbon content, it is very soft, thus, it is almost impossible to break the chips, and the build-up edge is easily formed on the cutting edge. Therefore, although its machinability rating is 80%, it is a problematic material to machine. It is best to cut steel 1020 with a sharp cutting edge to reduce the built-up edge. Rechameleometrined cutting speed range for turning at stable conditions is 300 to 405 meter per minute. Stainless steel is generally defined as an iron-based material that has a chromium content higher than 12% and is generally more difficult to machine than steel. Additional alloying elements such as nickel, chromium, molybdenum, niobium, and titanium provide properties such as corrosion resistance and durability. Higher chromium and nickel content tends to lower machinability. Stainless steels can be divided into 4 categories according to their metallurgical state. Austenitic stainless steel has a high chromium content lower than 20%. Martensitic and ferritic stainless steel has a chromium content of up to 18% with low nickel content. Duplex stainless steel has a 2-phase austenitic ferritic structure, combining the favorable properties of both stainless steel categories. In the table, cutting speed values suitable for carbide inserts are given for 3 stainless steel materials that are used extensively in the manufacturing industry. Since a single-point cutting tool is used in the turning process, the cutting speed value is slightly higher than in the milling process. The rechameleometrined cutting speed range for turning at stable conditions varies on average from 150 to 225 meters per minute. For example, stainless steel 304 is an austenitic stainless steel alloy with 19% chromium and 9% nickel. It is a simple chromium-nickel stainless with 0.1% carbon that exhibits excellent resistance to atmospheric corrosion but is not suitable for harsh environments. It is relatively easy to machine, compared with other austenitic alloys, with a machinability rating of 43%. ISO K material group is frequently used for sand castings due to its excellent flow properties. It can produce complex mold shapes, especially for the automotive industry. Cast irons have a carbon content of 1.8 to 4.5% and a silicon content of 1 to 3%. They have low melting points, high machinability, lower adhesion and strain hardening, and lower thermal conductivity than ISOP steels. Cast irons have low impact strength, similar to brittle materials, good thermal conductivity, good dampening properties, and ultimately, low hardness. Cast iron is machined without coolant. It is possible to carry out wet machining in order to prevent contamination. Chip morphology has a powder-like, short form or a continuous long morphology. Chip control is rather easy and power requirements low. Low cutting forces occur, short discontinuous chips are produced and the tool wear mechanism is usually abrasion in machining. The suggested cutting speed values can be seen on the screen. ISON material category belongs to various metals with considerably different properties, such as aluminum alloys, pure copper, and copper alloys. Magnesium is a lightweight, energy-efficient material with relatively high strength, good castability, generally good weldability, and high vibration damping. Aluminum alloys are mostly used materials in the ISON category and they produce long chips. Cutting forces, and thus the power required to machine them is low. The cutting speed values of two aluminum materials, which are used extensively in the aviation industry, are given in the table. Aluminum 6061 material is machined at high cutting speeds because it is softer. Aluminum 7075, on the other hand, can be processed at lower cutting speeds because it has a harder structure and contains silicon. Cutting force and power requirements are rather low and tool life is rather long, so higher cutting speeds can be employed, contrary to most other material categories. ISOS material group is relevant to heat-resistant superalloys and titanium, materials with high tensile strength and high corrosion resistance. These materials offer the best combination of corrosion, oxidation, and creep resistance at high temperatures for various chemical environments. For that reason, these materials are used in the aerospace industry in power generation, oil, and biomedical industries. The ISOS materials can be separated into three groups as nickel-based, iron-based, and cobalt-based alloys. Cutting forces and power required are quite high and chip control is difficult during the machining of these materials. Due to the low thermal conductivity of superalloys, cutting temperatures are very high, as well as cutting resistance and machinability are among the lowest in comparison to every material group. Titanium and heat-resistant alloys need to be machined with very low cutting speed parameters due to their chemical composition, high mechanical properties, and low thermal conductivity coefficients. The table shows the approximate cutting speed values used to machine Inconel 718 and titanium 6 aluminum for vanadium materials that are used extensively in the aviation industry. It should be machined with positive and sharp cutting edges. Geometries that are suitable for austenitic stainless steel will also work well on heat-resistant alloys. However, quality manufacturers will have different geometries specifically designed for nickel-based alloys in their catalogs. Hardened and tempered steels, for example bearing steel, tool steel, martensitic stainless steel, chilled cast iron, and hardened cast iron are included in the ISO-H material group. This is the smaller material group and is relevant only to hardened counterparts of materials belonging to other material groups such as P, M, or K. These materials exhibit higher wear and abrasion resistance, as well as oxidation and corrosion resistance, than ISOP materials, but with lower thermal conductivity. The appropriate cutting tool materials should exhibit high hot hardness and chemical stability, apart from strength, requirements which are met by few materials, such as PCBN, whereas also ceramic or cemented carbide tools can be used in certain cases. Low-medium depth of cut and feed is recommillimetrinded and machining ISO-H materials and the use of coolant is also suggested.